And it's live. I guess it doesn't mute everyone to start, so I'll go ahead and mute everyone else. Who else is left? And I think that takes care of everyone. Okay, so day 2. Let me bring this back up. So far, let me see if this is working. Q&A. You'll just be not working. All right, so we're going to go ahead and do, it'll be a bit more hands-on today. We'll be covering diodes and alternating current, as well as oscillators. And make sure that's working there. There we go. Cursor wasn't working before. I might have touched on diodes last time. Let's go ahead and review what we started with last week. And let me see if my colors are working. My colors are working, and I can make you smaller. Okay, so we covered Ohm's law. We're not going to be touching on this as much mathematically, so don't worry if you're not quite number inclined. Just know that voltage is, I'll go ahead and write this. Volt edge is current times resistance. And that's all we need to start with. So remember that in conventional current, we have a circuit. Let's make you a color here. All right, we remember that the conventional current flows from positive to negative, but the electrons, the negative charge, are really going this way. But for most of the day, we're only going to be concerned about conventional current. We're not going to need to worry about the electrons. And the reason why we don't worry about electron flow all the time, where we prefer conventional current, is particularly in semiconductors. So what is a semiconductor? Semiconductor is a series of elements. It's a group 13 metal, I believe. If you look at a periodic table, we'll actually take that out in just a second. We'll get into some chemistry behind it. Silicon is a very common semiconductor. It's called a semiconductor because pure silicon normally doesn't conduct, usually is not a conductor. And let me pull this up real quick. Notes, where are you? There's a few other semiconductor metals. We can use germanium and selenium. We're mostly concerned about silicon today. And silicon is very important to a component called a diode. Someone's unmuted themselves.
Oh, sorry about that.
And so in our diode, we've got, it's a two-terminal component, and we've got essentially, we're not going to call that negative and positive end, but we're going to call that cathode and anode. And a diode, what a diode does is only allows current to flow in one direction. In this case, current only flows, if you think of conventional current, it's from anode to cathode. and our electrons are really going the other way. So electrons only going from cathode to anode. So it's like a one-way valve for electricity. All right, and if we get down on a molecular level, a diode is made of two pieces of semiconductor. And where are you? Here we go. Two pieces of semiconductor, usually silicon, and we've got two types of silicon we're concerned about. We've got p-type and we'll use that color. Actually, I don't like that. We're going to use that. And n-type. All right, this all makes sense in a little bit. And the difference between p-type and n-type, p is for positive and n is for negative, because this piece of silicon is doped with a group 14. Actually, let's go ahead and look at a periodic table. It all makes sense when we look at the chemistry. Let's switch this here. I'll share my browser. There we go. Silicon. There we are. It's in group 14, excuse me, group 3 metal. And if I remember correctly, it has, this is not the periodic table I was using before. This is it. I like this one better. Silicon. Here we go. Silicon has on its outer electron shell, it's got four valence electrons. And to get it to conduct, we need to dope it with either one extra electron from something from the group next to it, usually phosphorus. So we'll take our nearly pure silicon and we'll contaminate it with we'll dope it with a bit of phosphorus. And phosphorus has one extra electron than silicon. So that'll allow for the free electrons. We have enough free electrons bouncing around in the silicon to carry a negative current. So that is what we call n-type. Yeah, we'll switch it back here. So a negative type is made of, where's my cursor? Uh-oh, my notes have, there we go, frozen almost. So we have a negative type that has the extra capacity to carry free electrons. All right, so we got our electrons here, and it's gonna bounce right through this way. So n-type only allows electrons to flow, and p-type is similar to n-type. It's also a piece of silicon doped with a different metal. In this case, I won't pull up the thing again, but to the left of silicon, that's in our transition metals, is gallium. So we have a small contamination of gallium on our p-type. And actually, I've got this wrong. Gallium would have one less electron. Yeah, I have this wrong. I have my configurations wrong. Phosphorus for p-type, that's right. So we've got silicon and phosphorus and silicon and gallium. All right, and this has positive and negative. All right, so our p-type silicon has an extra electron. Am I getting this right? I'm not getting this right. No, I was right before. Look at me, I'm going crazy. P-type, gallium, silicon, phosphorus. Doped with phosphorus. It's not a compound. It's just random. If you were to look at silicon on a molecular level, it has a crystalline structure, and so if we'd have, let's say that's our silicon, silicon, silicon. They'd be all packed tightly because it's a solid, and we just have one electron every so often, or one atom every so often be something else. Yellow back. And that's what allows for electrons to flow, or in our negative type, n-type. With gallium, which has one less valence electron than silicon, instead of having a free extra electron to bounce around, it has a hole. What colors there? There we go. So instead of offering a free electron to move from one side to the other to be a conductor, it has a hole where it wants an extra electron. It's begging for one. And when we put those two together, we've got a negative side that wants to give away its electrons, and our positive side that's hungry for them. And quite naturally, we end up with electrons coming in on this side, going through our n-type silicon and conducting in this direction, being pulled like a magnet to the p-type silicon and continuing on its way. So this is the conducting configuration of a diode, excuse me, of a semiconductor diode. And if we were to reverse that, let's say we have a higher voltage higher potential on this side than this side, and we end up with our electrons flowing backwards, it would conduct through the p-type silicon, and but there's no more holes for the electrons to go into once it hits the p-type and n-type junction. So this will stop conducting, and we'll have no electrons at our cathode. Or if we think of it as conventional current can only flow from positive to negative, which makes sense. Positive to negative. But can't go from a low potential to a high potential. And so we end up with our diode here. Diode's not hard to make. It's been used in semiconductor diodes anyways, have actually been around a very long time. They just weren't useful until around the 50s. If you've ever seen a crystal radio set, it has something called a cat's whisker detector, So basically you've got a conductor here, and it's attached to a wire which comes down to a point, and this is very sharp. It's sharpened on the end, and it sits on a piece of gallium, usually any type of semiconductor that's N-type, P-type. No, I was right. N-type. And the junction where the very sharp wire meets the semiconductor forms a basic diode. And that's actually where we get the symbol for a diode. It's an arrow pointing like that. It's because this here, the cat's whisker detector, being the point on the semiconductor. And later, for handling a higher current, we talked about this last week. We talked about vacuum tubes, or valves, as they're called in the UK. And a vacuum tube is just a plate for the cathode, which is heated, and another plate, which is cold. And because of something called the thermoelectric effect, this is all in a vacuum. For this to work, electrons will go from the hot cathode to the anode. So let's take a look at this as its function in a circuit real quick. If we were to have, pretty simple here, let's get some red color. If we went out to a higher potential, say 3 volts. Alright, so we got 3 volts, and we're going to put it through a diode here. How am I going to do this? Let's measure our voltage here. Measure our voltage, and we want to know how much current's going through there. We'll put an ammeter in series. And let's just say, for the sake of argument, we're actually going to wire our diode in backwards. So we're going to make this negative 3 volts, and this will be 0 volts, of course. So this is now getting into relativity a bit, because there is a lower potential here compared to our reference points, which is ground, which is 0 volts. Another way you can think of this is, well, this is the supply, and this is really 3 volts positive. And this is really, if we make this our reference point and call that 0 volts, then we've just reversed the circuit, basically. But let's do it like this. Voltage we'd read here would be 0 volts, and we wouldn't get any current either, because, remember, a diode only conducts in one direction. And so because our current would be reversed, this is the higher potential, our current would go this way, and it would be blocked by this diode. And if we turn this around and make this end our anode, and this is our cathode, have a positive potential, we'd end up with not quite 3 volts. There would be a drop depending on the type of diode. This is not a perfect conductor. It would have some sort of voltage drop in it, and we wouldn't get quite the same current capacity as well. So we get less than 3 volts and less than I, because some of that, because of Ohm's law, which actually is a bit different here. It's not, this diode is not an ohmic device, but we will get less current than what we put through. And where a diode becomes particularly useful is in rectifying alternating current. So up to this point, all we've been talking about is direct current. Our electrons are always flowing in one direction, our current is always going in the opposite direction. All right, it's always conducting from a higher potential to a lower potential, conventionally. But now we're going to have to deal with alternating current. So let's make an alternating current source, voltage source. Boop. And we'll just get this here and this here. Alternating current is what comes out of your household outlets. Let's do this. Let's say it's, we'll rate that 15 volts AC. All right, so we've got, if you were to look at a graph of this, we're going to make a graph here, and we've got, say we've got our graph, this is voltage on this axis, and this is 0 volts here. So this is positive voltage and negative voltage. All right, and we got a reference point here. Let's just, it's ground referenced. And our y-axis here would be time. And if we were to make a graph of our household domestic current, it would be a sine wave. And that's a really crappy sine wave. You get the idea. Oh wow, what did you do? Stupid tablet. Alright. Alright, so here's one period of our... Oh, that's too thin. This is one period. That's a capital T. Alright, and domestic current will be, it'll be a sine wave at a frequency, depending on where you are. In the US, it's 60 hertz, or 60 cycles per second. All right. And let's say we wanted to turn this alternating current into a direct current, like what we get out of a battery. There's a lot of applications where we have to use DC opposed to AC, alternating current. So we want to rectify this. We're going to go from 15 volts AC means peak to peak. Actually, we got the RMS value. We're going to have to go into RMS now. So because it is a sine wave, we're going to be dealing with root mean square. So this would be about where 15 volts is. We call it 15 volts AC because of a property inherent to alternating current and sine waves. If we were to measure this peak to peak, we'd have to calculate it, but we'd be in the ballpark of something like 20 volts. Let's see. So with alternating current, our RMS values, our voltages will depend on what kind of wave the waveform is. Since it's a sine wave, let's just write this. In DC, come on, change. In DC, let me make you bigger. DC, the equation's pretty straightforward. Just whatever you put in, that's what you get out. But with a sine wave, we'd end up with... I'm busy.
You're busy. Go away. I don't like you. Go away. I'm busy.
You.
Go away.
Pardon me. It's a bit different. It's this neat little function. I know we wouldn't talk about maths very much, but this is important. Ft, and our equation would be slightly different to find root mean square. It'd be a over square root of 2. All right, that's all we need to know. So our input voltage, our RMS value, RMS voltage is our voltage amplitude, which would be peak to peak. So we'd measure from here all the way down to here. Peak to peak. We plug it into this equation, a over square root 2, and we get our RMS value. So in this case, it'd be what, 15 volts AC equals a over square root 2, and we multiply that by square root 2, which is 1.4. Yep, ballpark 21 volts. So this would be 21 volts. Minus 21 volts. Alright, so we want to change our alternating current here into direct current. So to do that, we're going to use our handy little diode. If you remember, a diode only conducts in one direction. So what we'll do is we'll have a diode here. It'll conduct in the positive half cycle. And since it doesn't conduct the other way, here's the voltage is changing direction. We'll have a negative voltage down here on this half cycle, and it'll stop conducting. So we're going to need at least 2 diodes to be able to rectify our current, our alternating current. So we got 15 volts AC. And we'll go with red. So at least somewhat consistent. Alright, so we got our AC voltage. Wow, that was a lovely circle. I've also seemed to have lost opacity, but yeah, whatever. Alright, so we got our that there. And this here. And let's put a diode here. And put a diode here. Let's see what we get in. So we know we get a sine wave like this with our reference going through 0 volts. But if you put some diodes here, This, come on, work pad. There we go. We know that our diode will only allow current on the positive half cycle to flow this way. And on the negative half cycle, because this would have a higher potential than this side, we'd get our potential going this way. This one would conduct, this one would stop conducting. And we're going to end up with, if we were to measure our waveform between these 2 points, we'd go from our sine wave at 0 volts potential, and we rectify that so that we only have positive cycles. Actually, I think we'd only get half of a cycle. Yeah, we might only get a half of a cycle. So we're going to actually need a full 4 diodes. Because in this case, we're only going to get the positive cycles. All right, so to get all of them, we're going to need 4 diodes. And it's going to look like this. So you've got our AC voltage source, and that's crooked. Not that it really matters. And we want to force all our potential up to a single point. So we're going to have that there, have that facing away, have a diode there. We're going to have diode this way, and a diode this way. So ideally, no matter which way the current is going, we'll end up with a negative potential here and a positive potential here. Actually, we've basically just constructed a power supply. We call this a linear power supply. We'll go ahead and add some extra filtering. And then we'll have a DC voltage available here, which we can then put through a load of some sort. This is our AC. So normally on this side we'd have a transformer. I don't know if we talked about transformers. Yeah, transformers only work on alternating current. Yeah, we'll cover transformers. Be able to make a power supply by the end of this. We'll give it a core. Right, so this is what our schematic symbol for a transformer looks like. You probably used transformers before, those big ugly things that plug into a wall. That's basically this circuit here with the transformer. What a transformer does is we take the ratio of the winding. So this is just a wire wrapped around some sort of ferrous material, usually iron. Use an iron core, right? And we've got another secondary wire wrapped around the same core. And we know that creating a coil like this and applying a current. It will just go there. Will induce a magnetic field. We'll end up with magnetic field all around here. Either side, omnidirectional. This is the basic for electromagnets. And since we can go from an electric field to a magnetic field just by making a coil of wire, we can magnetically couple this inductor. This is called an inductor, basically. We measure inductance in henries. And we generally represent it with an L. What does L have to do with henries? Absolutely nothing. It's actually named for Lorentz, who had a lot to do with inductors as much as henries, or at least as the science behind it. And so we know it creates a magnetic field, and we can couple that to another inductor. Where did my thing go? Come on. Make me another color. We'll go with that. You need to be thicker. And because these are both sharing the same magnetic field, the magnetic field that this coil creates will induce a current in this other field, in this other coil. So if we have current going this way, it'll create current in the same direction. End up with another current over here. And what makes transformers useless? Useless. Well, this useful. Let's see if I can articulate tonight. In this case, if we have the same number of windings on this side as we do on this side, then whatever voltage we put over here on our primary, if the ratio of these windings are the same, then we'll end up with the exact same voltage over here. But what makes transformers useful is if we change this ratio and said, let's say we have 10 times as many windings on this side as we do on this side. Then whatever voltage we put in on here, according to this ratio, we'll get a tenth of the voltage over here. So let's say there's 100 volts. Oops. 100 volts over here going through this transformer. It would have to be AC. We'd get 10 volts over here. And this is a configuration we call, we're not talking about, that's a transformer now. This is a configuration we call a step-down transformer. And we normally at least try to represent it. What is going on? This tablet. Okay, I don't know why my opacity's changed. Brush. Brushy, brushy, brushy. Yeah. Where's my brush dynamics? Zero opacity, please. There we go. Oh, that'll be easier. Alright, so this is a configuration we call a step-down transformer. So we'll usually represent it like this, and we'll go, alright, it's got a core, and it's got not so many windings on the secondary. Here we go, call this side the primary, and this side is secondary. Now, these only work on alternating current. These only work with AC. There was sort of a battle of the currents in the early days of electricity between most notably Tesla and Edison. Good names to know. Tesla actually worked for Edison for a while. Edison kind of took advantage of him. But Edison didn't have the mathematical background to understand the physics and equations behind alternating current. It didn't make sense to him. And Edison pushed for direct current in the homes, and Tesla obviously found out that AC was better because of electrical losses. So with DC, any sort of conductor will have losses. It'll be, nothing is a perfect conductor. It'll have an inherent resistance, and we know how to find that resistance. And because resistance is never quite zero, according to Ohm's law, the voltage that we put in on this side, we're going to get a lesser voltage over here because of voltage drop. Where'd you go? Here you are. So the only way to overcome this equation here, because of Ohm's law, this restriction with voltage drop, if we can have a really high voltage, assuming resistance is constant, we can decrease our current and we'll have less losses over here. And an easy way to do that is with a step-up transformer. Just like this, we just change our ratios. So our primary would have less windings than our secondary. We got, oh, that's awful. And so let's say at our generator here, we've got a source of 100 volts, and we step it up 10 times in a 1 to 10 step-up transformer. We end up with 1,000 volts over here. This is basically how transmission lines work. And it would travel over incredibly long distances, relatively long distances, to get to your house. And then we'll step it back down again to make it useful. To run our light bulbs and appliances and so on and so forth. Typical domestic voltage in the US, it's 110 or 120 volts. Call it 120. And we get 120 over here again too. And we lessen our losses since we have a higher voltage. And let's see. Any questions so far? Any of this at all confusing? we put in our, let's draw our current lines here. We put a current in this way. The current's actually, since it's alternating current, it's going back and forth, but we'll think of it as one part of the cycle. Then we'd get the same current going this way, and the same current going this way. And the reason that we need AC for this is because of a problem inherent in inductors. What will happen is you'll apply a current, all right, and it'll generate a magnetic field, and it'll keep that magnetic field, but it'll end up saturating. It'll get to a point where it can't make the field any bigger, and it's only from the change in let's see, magnetic flux. Not sure what the symbol is for magnetic flux. I probably should have written that down. Phi. It's a capital Phi. It's only from the change in magnetic fields that we're able to go from electric to magnetic and back and forth again. I've got a lot of dings going on. All right. Any questions? I don't see any questions. How long have we been at this? Nearly an hour. Let's go ahead and take a break. I'll unmute everyone. I don't know how to do that. I think you have to unmute yourselves, actually. We've got our happy little diodes. No questions?
Nope, no questions from me anyway. I don't know about everyone else.
I'm thinking Greg fell asleep when he got home.
That's a strong possibility, actually.
The only reason I know he's not in here is because when I went into the chemistry of silicon, he didn't correct me. So.
Yeah, okay, that makes sense now.
All right, well, if we don't have any questions, the bloody Q&A app was working. Go ahead and move on momentarily. I'm still getting lots of dings. I am in there. Oh, he's watching, apparently. I don't see him. Users. Nick C, Nick N, Nick J. Yeah, I just have Josh, Nathan, and Chris. But I guess he's listening. All right. We'll go ahead and move on. So we've got. Oh, is that Nathan?
Huh?
Hi, Nathan.
Hey, what's up?
Hi. Where am I with my...
I'm doing my best. I only understood some of it.
Hopefully it'll make some sense. Flux. All right. Oh, come on. There you go. All right, we'll go and move on to transistors real quick. Transistors are really important as far as computers and modern electronics are concerned. A transistor is, well, let's start with what it was with a tube. So we remember our vacuum diode, our vacuum tube. Yeah, let's choose yellow. I'm getting all sorts of messages here. All I could find was the YouTube live. Oh, well, I guess I could pull them in the Hangout here. Alright, so you remember our vacuum diode. And why did I draw that? That's correct, actually. But not what I wanted to do. Alright, so we've got our cathode here, which is heated up. It's hot. And our anode, which will be a different color. And let's say we put a grid in between. Put a conductive screen in between these two. And we'll have a terminal there. Alright, so to get electrons to flow from here to here, normally because if this screen isn't connected to anything, it'll work just like a diode. And we've only got our electrons flowing from cathode to anode. Right? Or if we had this connected to an electron source, which would make more sense actually. So we've got this set ground potential of 0 volts. We've got this set ground potential, 0 volts. And we've got a positive potential over here. Actually, just connect something to it. Let's look up a light bulb. That's a crappy light bulb. Oh well. And we've got we've got to have a lot of voltage for this to work. Alright, so we've got our electrons going here to here, happy flowing, but if we were to put, I think Greg's come unmuted. No, someone's unmuted. Chris, you're unmuted. I'm going to mute you. But if we give our control grid a place for electrons to go, opposed to the cathode, we can redirect our electrons. We can put this at a we'll give it 50 volts. It doesn't have to be quite as much. If we give it a path for the electrons to follow, there are electrons now, instead of conducting to the anode, they're going to be shunted away by our control grid. Oops, you're not supposed to go away. And I have to keep making sure there's not messages in there. Alright, so this is our basic, we've created, instead of a diode, what we call a triode. I actually have a triode here, if anyone cares to see what it looks like. Let's see, switch you to camera. Alright, and I'll bring you over here real quick. Here we go. This is a Type 24. This one is circa, it doesn't have any sort of date code stamped, but this style tube was manufactured from 1927, 28 or so. But this particular style didn't come about until the 30s. And they stopped making these right around 45, 50 or so. They were a lot manufactured. And basically, I don't know if you can see inside there, but we've got, you can see on the outside, this metal cylinder is the anode on the outside. And on the inside, there is a similarly rolled shape. It's hard to see on the camera, but it is in there. Right inside, there is a similar rolled conductor, and then in the middle, there's another one even smaller that's connected to the filament wires, and that just heats it up. So that's a cathode inside. And our anode is actually connected on the top here. That was a nice little field trip. We'll go back here. Greg, I suggest you make proper use of the Q&A app, please. Use the chat if you want to voice your opinion. That was before I was in here, remember? No, well, I missed that. I'm sorry. It was probably the chemistry part, wasn't it? Moving on. Oh, so the Q&A app works in YouTube, but not here. Good. All right, so we've got our basic triode here. And let's look at that in silicon form. All right, so semiconductor equivalent of a triode is a device called a transistor. And we've got two different types of transistors. What our schematic symbol looks like. All right, and we've got this guy pointing in. All right, so up here, just a quick aside, it's not really important, but this is the cathode, and this is the anode, and we call this the grid in between here. And the grid controls current flow from cathode to anode, or anode to cathode. With tubes, it makes more sense to think of electron flow opposed to conventional current. But with semiconductors, we will definitely be thinking of current. So a transistor is basically a type of switch that we can turn on and off electronically. So a voltage induced here allows for current to flow between these two terminals. We've got names for all these terminals. We've got, we'll use our not so special color. This is the base. This is the collector. And this is the emitter. All right. Similarly, this is a bit different here. This is the base, this is the emitter, and this is the collector. All right, and we've got two different types of transistor here. This is NPN, and this is PNP. If you remember back to our diodes, where we have negative type silicon and positive type silicon, where we have silicon that's doped with either an extra valence shell or an extra electron, an adjacent element. And so transistor is pretty simply just a bit of N-type silicon in a channel of P-type silicon, and then another bit of N-type. And these are all our electrodes here. We've got that, got that, and we've got that. And these correspond to our base, our collector, and our emitter. If I'm not mistaken. All right. And so in a basic circuit involving a transistor, we'd have, let's put it over here. We'd have, let's say we have a small voltage. Let's see if I can make lines today. Here we go. No, we're going to make you a light bulb. Ah, good job. And we got positive, and we got positive, and negative. All right, so in our basic little circuit here, we've got a small voltage driving the base of our transistor, causing it to switch on and allow current to flow. So we have a small current between here, and actually it'll go like this. A small current there, which will switch on our transistor and allow, make you bigger, a large current to flow through the light bulb. Or, if instead of having a battery here, we emitted this, and this was at 0 volts potential, our transistor wouldn't conduct, and our light bulb would not light. Pretty simple. And importantly, because transistors can use a small current, a small signal, small voltage, to control a larger current and a larger voltage, we can use this configuration as a type of amplifier. It's pretty common use for transistors. Oops, we're going to use an N-type transistor. Oops, arrow inside. Oh, that's just getting worse and worse. There we go. Alright, so a small signal into here will produce, if we have it connected to a capable enough power supply, will create an amplified signal at the output. It'll be identical, just higher amplitude, almost identical, depending on the properties of the transistor. So those are the two basic applications of a transistor that we're worried about, is as a switch or as an amplifier. I've got another ding. Any questions? We're going to have to look at our circuit here. Where are you? Image. I'll go ahead and draw it out. This is a circuit I'm going to be building today. These are pretty easy parts to find. I posted a parts list. I'm going to take a look at its design and how it works. Yeah, it's not big enough. Mm-hmm. And we need one there. Alright, and you've got an iron core. Oh, come on. A type of diode you're probably familiar with is the light emitting diode, or LED. I'm going to be using one in this circuit. An LED symbol looks a lot like a normal diode, but we've got some light coming off of it. Alright, we'll just say this is 0.5 volts-ish. Actually, that's bad. That might mean AC. So we'll go, probably down to 0.3 volts. All right, and positive and negative. Right, so this is the type of circuit. This has a value of 1 kilo ohm. This is a circuit called a Joule Theif. Yeah, whatever. And it's not very many components here. We have a battery as a power source, a single resistor. This is a transformer, and it's a 1-to-1 transformer. We'll look at that in a second. And a transistor, and our load is an LED. So the thing about LEDs, I'd mentioned that all diodes that aren't ideal diodes have a voltage drop. So if you were to put a current through a voltage, through a diode, excuse me, you'd end up with, if you were to measure the voltage across the diode, you'd get something around generally 0.3, 0.7 with typical rectifier diodes. It could be as much as 1.3. It all depends on the diode design and how much current it's meant to handle. LEDs, in particular, require quite a bit of voltage to turn on. They'll require about 3 volts to turn on. So if we only have a 1.5 volt battery, like a single AA, we're not going to be able to get this to light up. Let me show you that real quick. I don't know how well this will work, but I'll show you some things on the workbench. Let's go and switch off view. We got a camera. I think I can get it closer, maybe. We'll go there. And is this too blindingly bright? Yes, you are. Alright, let's see. I can move you down, probably. As far down as you'll go. And left. Oh, good. It's switched off. Well, I wish I could show you this.
Zach,
Yeah.
Zach,
Mm-hmm.
are we not going to be able to see?
I'm working on it. Your camera, the connector is bad or something.
Okay.
Let me get it back up on Hangouts.
Great.
I don't know how to get the video back here. Oh, come on. Ah, well, this is bad. Oh, settings, no. Well, apparently it doesn't let. Oh, wait. Here you go. UVC camera, please. Right, let me try closing this. Let me try one more thing and then I'll give up or try a very unorthodox solution. Alright, unorthodox solution it is. Is this still working? Yeah, it is. What's going on? There you are. Say hello to one of the most happiest things I've ever done. If you'll do it. Oh, you're not going to do it, are you? Oh my goodness, there it is. Alright, this is... with my finger, here we go. And I might be able to make this full screen. Ah, yes. Alright. There it is in all its awfulness. And I just can't breathe on the camera, or it'll ruin everything. Alright. So, we're gonna get hands-on a bit here. Alright, so here we got this is the type of LED right here. So I can start the camera. And it's blurry. And focus on focus. This is not sure which color this is. We'll have to light it up and find out. But it is a diode, and LEDs to indicate which side is anode and cathode, which side's positive and negative. It's got a flat side on it. And the flat side is the cathode, is the negative side. It's also a bit shorter. I don't know if you see there. It is the shorter lead. Right, and we're going to have to do some math. So I know that to light this bulb, to light this LED, I'm going to need something around 3 volts to light it up. And I don't have 3 volts readily available on my benchtop. I've got this power supply here. It gives me 5 and 12 volts. So let's use 5 volts, and I know that 5 volts is probably not going to be good for this LED. If we put too much voltage through it, because that will imply there'll be too much current going through it as well. And if we don't do something to take care of that extra current, we'll end up blowing up our LED. It'll burn out. And we don't want that, because LEDs are a little pricey. When I say pricey, I mean 30 cents. But we don't want to have to go out and get a new one. So we're going to have to find out what value resistor we're going to need to safely power that 3 volt LED. So I'll switch it back here. That's suddenly become easier. There we go. So we'll just do our calculation real quick. You know that E equals IR. Right. And so we have the 5 volts. We have the 5 volts are 3 volts that we get from the LED minus whatever voltage is left over and need to dissipate. Right? So we solve for V there. 5 minus 3 equals IR. And remember that with this particular LED, I know from the data sheet it needs 30 milliamps. or so. So we want to limit it to 30 milliamps. Let me think this through. Actually, 50 milliamps would be good. That'll work out nicely. 50, 20. Yeah, let's be on the safe side. Do 20. So 2 volts equals 20 milliamps is 0.020 amp. R. We need to find our resistance. Pretty simple. Solve for R. Not 20. It's not working. 0.20. Cancel those out. And R should be 100 ohms. There we go. So we need to limit our LED here to 20 milliamps. I'm blowing up and doing a video about that. There you go. Right, to limit that, we're going to need a 100 ohm resistor. Resistors are denoted by a color code. It'll probably be easier to look this up. Basically, on the resistor, we have 3 or 4 color bands, and each band indicates the value. And so, according to this chart over here, we have first value, first digit, second digit, and then a multiply. So for 100 ohms, that'd be 10 times 10 to the first. Yes, 10 times 10 to the first. And we go over to our chart here and find out that the color code for that would be brown, black, brown. And so I've got that on my resistor here. Probably impossible to see. This camera's focus is horrible. Come on, camera, focus. Focus. I am all you see. It's not going to focus. Oh well, just believe me that this is a brown, black, brown resistor. We're going to put it on I'm going to put it in a breadboard here. This is a something we use for prototyping. Each 5 contact row here is connected to each other. I can just push these in like that. We've got our 2 components. Really hard to see. Looks like I use my phone as a second camera. Get it in the Hangout. Yeah, we'll revise this for next time. I hope that everyone can see decently. Alright, so we've got our resistor put in here. Let's find out some light. Get them back out. There we go. Got a resistor in there going through our LED. And I'll just hook this up to my power supply here. So I've got green as negative and yellow as the positive. And we'll cross our fingers and hope we don't blow it up. Oh, there we go. It's amber. Right, works for me. So our calculations, we can double check our calculations with real world application. I'll take my voltmeter here. I'll go ahead and bring this up so you can see it. All right. I'm going to take the voltage across. We know that the voltage across the resistor plus the voltage across the LED should be, very careful here, should add up to whatever our supply voltage. So let's take our supply voltage first. Measure across those two terminals. We've got 5.12 volts. All right, so we're going to measure across our diode first, or LED. We got 2.01 volts plus across our resistor. Oops, get the right polarity. 3.09 volts. 3 plus 2 is 5. Alright, so we did our calculations correct. We could also check, I'm actually probably going to have trouble with this because I've blown the fuse in this multimeter. So we're going to have to settle for a bit of a loss of precision here. We're going to hook this up as an ammeter. We're going to count the electrons, basically, count the current as it flows through our circuit here. And it's reading 0.03 amps, which is in our ballpark of 20 milliamps. It's pretty close. This is kind of a bit of a kludgy instrument I'm having to use. Actually, I might have an analog meter. Would it work? I go through multimeters like candy, by the way. Not good. Could be improved. Alright, so we've got what? 50 milliamp scale. We'll start on the 250 scale. We're not going to be able to see this very well. I'll just jack it in and we'll have a look at it. So we'll go there. I should be able to go here. There. What? It looks like this. Alright, well this multimeter, because it's analog, it's consuming all the current. That's interesting. It's consuming almost all the current trying to measure it. This is no good. Alright, so interesting bit about, oh yeah, that's why. Alright, so this is an analog meter. This is digital. So multimeters, in order to measure voltage, what it does is it's got a high value resistor in it, and it'll measure the voltage drop across that resistor. I'm sorry, to measure current, it'll measure the. It's got a low value actually. Yes, voltage is high value. All right, and that way it's almost like an open circuit. It depends on the meter. Usually it'll specify. This one does not. It'll specify an input resistance. And to measure current, what it'll do it'll take a low ohm resistor, a relatively low value resistor, and measure the voltage drop across it. And in a digital voltmeter, that can be really low, like sub 0.0 ohms. In an analog meter, it depends. This has an input impedance of 2 kilo ohms per volt DC, and apparently that's enough to shunt enough current away from our little 20 milliamp LED that it will no longer light the LED, and we won't get an accurate current draw. So we'll just have to settle for a 0.03. That works for me.
Apparently Josh got dropped.
Alright, so we've got
Some
our
other guy did.
LED lit on 5 volts. Actually, it's be 3 volts across. That happens. He's on his tablet, I think. Any questions?
Yeah. It's just us three now.
We lit an LED. Right, but now we're going to do something. Alright, that's fine. Now, let's say I wanted to... I've got this battery here. I want to light this LED from this battery. And this is a... Let's go and measure the voltage across here. I took this out of... This is actually what would be considered a dead battery. It's... no, it's not a bad battery. It's actually completely good. We'll use it anyways. It's measuring 1.55 volts, which is actually what it's rated for. Funny, the thing I took it out of thought it was dead, so we'll look at that in a second here. Let's try to light that LED I have from this battery. So we'll go ahead and make it easier here. I'll use a clip lead. Go and clip the positive side, if I can figure out which one it is. I'll hold it to the terminal there, and we'll try to complete the circuit, and it's not doing anything. You know, we need like twice that voltage to light this LED. So what can we do? Well, we're on DC, so we can't use a step-up transformer. That would be an obvious solution. If it was AC, we could do that. But we've only got direct current to deal with here. So what we can do is we're going to have to find a way to step up that DC voltage. We're going to do that with basically creating alternating current. And so the circuit we're going to make is called a Joule Theif. We saw the schematic earlier. Let's go ahead and look at that. I'll explain how a Joule Theif works. Yeah. So here's our battery, right? So this is a transformer. It's basically we got a wire, this wire around here, and this wire is in the opposite way. It's in parallel, right? And they're both coupled by a donut shape, toroid. Alright? What a toroid does is, remember that a coil, it would probably help if I had the microphone over here. Remember that a coil of wire will induce a magnetic field. Make sure everyone's muted here. Where's everyone? Oh, toolbox. Why aren't you working? Alright, remember that a coil of wire will induce a magnetic field. But if we wrap it around something that's ferrous, or ferromagnetic, iron, for example, that's where it comes from, ferrous, Fe, ferrite. Instead of the magnetic field being produced around all of the inductor, it'll be contained in the toroid there. There's a magnetic field, and just for we have our, oops, you're not red. Red. We have a wire wrapped around our toroid. Alright, and it'll create a magnetic field, but the magnetic field will only stay inside the toroid, where it's wound by the wire. Alright, so there's a few things that happen in this circuit when it gets powered on, when you connect the battery. All right. So as soon as you connect it, let's see, color here. Blue. All right, we have our current flow this way, and it'll go through. It has two paths to go through. All right. On DC, an inductor is just a piece of wire. It's going to flow through here. It's going to go through our resistor, and it's going to energize the base. Actually, before it even does that, it's going to create a magnetic field inside here. Same thing with this one, because it's got two paths. All right, current flowing this way. All right, so we'll create a magnetic field, and we saw our donut up here. And actually, if we follow this all the way through, we know that there's not enough voltage here to light up this LED. So there actually won't be any current flowing on this side. It'll take the electricity always follows path of least resistance. And so in this case, our transistor switching on provides a path for current between base and the emitter. All right. So current will flow through here. It will build up our magnetic field inside the toroid. All right. And as this magnetic field is increasing, all right, so long as delta V is positive, or our magnetic flux is rising, all right, and it'll rise until it reaches saturation. There'll be a point where the magnetic field can't get any bigger inside that toroid. And while it's changing, it will also be inducing its own current. Use across here, but our transistor isn't turned on. Actually, our transistor is on at this point, or is in the process of turning on. So the current following the path of least resistance will just drain back to the battery. And eventually, once this magnetic field inside our toroid, our little transformer here, is completely saturated, it'll reach saturation. It'll turn this transistor fully on. Right, so now we have the availability for current flow either through here, because this will have a lower resistance than the diode. Our magnetic field will saturate, and at this point there's nowhere else for current to flow, so our transistor here will snap shut. Alright, that's actually a little more pronounced, like this is what we'd see if we were monitoring the base voltage right here. It'll close. This magnetic field will collapse, and as it is collapsing, it's inducing a change in this coil, which will create a current here. Let's get a color. Right, so we've got it collapsing here. The magnetic field will collapse much more quickly than it was built up. So we'll end up with more current flowing here. And because of Ohm's law, we'll also have more voltage. Alright. And by this time our transistor has shut off, so no current can flow through the transistor. The only place for it to go is through our LED, and it'll flash, it'll turn on, use a turn on color, it'll turn on until all the magnetic flux inside this transistor, or inside this toroid, is depleted and turned back into electrical energy, and our transistor will turn on and off that quickly until this is all unsaturated. The transistor is not conducting anymore, and then the cycle starts over. So we end up with our LEDs actually flashing. It'll be flashing, but it'll be flashing so quickly we won't be able to see it. So we've got our 1.5 volts DC coming in, and what we're doing is this circuit will chop it up, and we'll get twice the voltage out, but it's only on half the time. So contrary to the name, we're not actually stealing any power, because the power in this case, since it's current times current times voltage, if we look at our graph here, the area under the curve here would be the same on the output. So we're not stealing any power, we're just using it more wisely. So we'll go ahead and build it. I'll show you how to. It's really easy. These are all mostly parts you can find at local RadioShack, or just actually you can probably find most of these parts out of salvaged electronics. So go ahead, and I've got one built up here. We'll start over. Let me see if I have an extra coil. Don't have one the right size. Alright, I'll go and tear my beautiful work apart. Boo-hoo. Really easy. Parts you're going to need for this. I'd recommend a breadboard to build it on if you don't have one, but if you don't, if you have one, if you don't, it's not necessary. You can just build it by twisting the components together. Right, and this will probably, you'll need a transistor. This is a transistor package. Transistors come in different size packages. This is a TO92. It's a very common package. We call it through-hole construction, because on a circuit board, these leads would go through the circuit board and then be soldered on. Anyways, you're going to need any NPN transistor. I believe this is a 4401, a 2N4401. I'd recommend this one, but any sort of signal transistor will work. 2N22, 2N2222, actually, that's what it is. It's a very common switching transistor. You also need a 1 kilo ohm resistor, and the color code for that is brown, black, red. We'll need the LED that we want to light up, either one. I'm going to use this one that's diffused. And this will probably be the most difficult component to find. It's a toroid. What a toroid is, this is a big one, but probably easier to see. The ring of a ferrous metal. It could be, actually this might be an iron core. So if you can't find a toroid, you can probably improvise with just a nail, an iron nail, or a screw. Screw would work well. You're also going to need some wire. Any thin sort of wire will do. I'm using a solid core. This is 0.9 millimeter diameter, and it's got two wrapped together. You can just get whatever. Or you can also, other thing you can do is Cat5 or Cat6 Ethernet cable. Just if you have a length of this, what you can do is just store. Let's cut off some first of all. You'll need about 30 centimeters of it, 30-40 centimeters, and we'll take. You can take a hobby knife and just very carefully score down the outer shield here. This here. Keep it open. Or if you have wire strippers would be able to get this off too. You just need to be careful. Careful either way. So you'll slice your finger open, the other way you might slice into the wire underneath. Just very carefully score down, and you'll be able to open it up and reveal the wire inside. We're just going to take some of that out. There we go. We can get to it a bit easier now. And you can grab this this fiber. There will be a fiber inside, and score down. Just pull it, and that'll cut the rest of the outer shield. It's nylon or something, some sort of crap. And we'll be able to pull the twisted pairs inside. And discard the shield. There'll be 4 wires inside. And we just need one of them. It doesn't matter which, but I think the brown one. The brown one's the least twisted. So pull that out. And when we wind our transformer, our toroid, we're going to want it unwound. So go ahead and unwind it. Keep it together, but unwind it. We'll have it apart there, and we'll have our 2 conductors. I'm going to reuse what I was using here. Unwind this. Anything will work. So we'll take our 2 wires. Right. I've undone that. I've got 2 wires, and all you want to do is take one end, and we'll twist them together. Nice to see. We want to keep them parallel as we're winding this. So it's pretty easy. We're going to take our little donut shape here, go through. So the first time through, that's 1 turn. Alright. We're going to do it this way. Alright, so we got red and white. And we'll do another wind. Put both wires through. It's pretty easier actually if I go the other way. This one, here we go. Right, and we'll just pick a direction and we'll go around the toroid. Go through again, and we're going to wind it about 10 or so times. Just fit as many as you can. It's important that while you're winding it, can't do like what I did. You need to make sure that they alternate between the two colors. You can use any wire. If you use the same, I would recommend using two different colored wires. If you use the same, make sure that they stay on their own sides while you're winding it. Alright, so we've got two winds there. We'll go through again. So two colors. It's really easy. Just make sure they're going red, white, or whichever two colors you have. And pull it tight. It should be right up against the toroid there. And we'll keep going round and round. Isn't horribly critical. You want to keep them. It should be evenly spaced by the time we're through winding it, but just 10, 11, 8 to 11 or so windings should be good. And there we have 1, 2, 3, 4, 5. That's 6. 7. 8. Oh, don't go risky. 9. I think we can fit more wind on here. Sure. And 10. There we go. Once you've wound it, just kind of space the windings out as evenly as possible. And try to keep the windings together too. Right, so you've basically just wired a little transformer here. Now what we're going to do is we're going to take, you've got two pairs of two different colored wires. You're going to take a wire from one side and an opposite colored wire from the other. So we'll take a red one and a white one from either side. And we'll twist those together. So combine there. Right. And I look back at my snap. Alright, so the pair we twisted together will be connected to the positive side of our battery. Right. And then we'll build the rest of the circuit on our little breadboard here. Start with the transistor. Our transistor it'll have a flat side. It's kind of D-shaped. D-shaped transistor. The flat side, if you put the flat side to your right, then the leads are emitter at the top, base in the middle, and collector, opposite. Collector at the top and emitter at the bottom. So that our breadboard here matches our schematic pretty closely. We'll go ahead and put that into our slots here. Just form the leads with your fingers to span. If you're doing this on a breadboard, just spread them out and put them in so they're in every other row. That usually leaves enough room to work pretty nicely. So we've got a transistor in. I'll put it a row over so that I can access that contact right next to it. And let's see, we're going to need our 1K resistor connected to the base. So I've just got that so far. Got a resistor. Remember the rows of the breadboard are all connected. So our resistor is connected to the base there. Our LED will find the negative side, which is the flat side on the plastic, or the shorter lead, and we'll put that so the long leads at the top and the short leads at the bottom. We kind of keep positive voltage up top. There we go. Positive voltage up top and 0 volts or ground potential on negative lead at the bottom. And it'll go straight across the collector and the emitter of our transistor there. Right, and then finally, looking back at the schematic, we're going to take our toroid. We twisted 2 of the leads together. And it doesn't matter which one we use, but one needs to go to the base, and the other one goes to our resistor, excuse me, and the other one goes to our collector of the transistor. Right? And that's it. We've built it. Now it's time to test it out. And just to prove that this isn't a special LED, I'll power it off of this supply here. You can see it light up. You know it works, and we know it's the correct voltage to work in this circuit. It's a 3-volt LED, and it definitely will not light up on our battery here. So nothing. Not even, you can see that. Not even a flicker. Alright, I just improvised for a battery holder here. I took aluminium foil and a rubber band and gave it some nice little terminals to hook clip leads to. These are nice for prototyping. And so we'll go ahead and the flat side of the battery is the negative terminal. It should be labeled, and the top would be positive. Yeah, see, there we go, positive. So we'll respect our polarity, and we'll connect the collector of our transistor here. We'll put our LED back in. Where did our LED go? Oh, apparently, there it is. Put our LED here, and put it back in our circuits. Make sure I've got those in the right slots, and no, they are not. Our circuit would not have worked. Then, here's our moment of truth. Then connect the twisted pairs of toroid to our battery. Let's check our battery voltage real quick. Check. 1.5 volts. Ta-da! It is actually lit. Kind of hard to see. It is actually working. What do you know? We did something. We made a thing. Let me try a few other LEDs. Oh, this one's smaller. There we go. pulled it up. Look at that. It actually works. All right. Now to further understand how this works, we're going to use a piece of equipment called, actually, first of all, if we were to take our, so in theory, the voltage on our LED here should be enough to actually light it up. Clear some room here. We'll go ahead and take our voltmeter here. We'll set it to DC volts, and we'll measure across here, across our battery, and nothing's going to happen because I have it connected wrong, and it's acting like a short circuit. Alright, so we'll measure across our battery, and see, look at that, it's dragged the battery voltage down all the way to 1.15. This is a very dead battery. The 1.5 we got earlier is probably just from it sitting for so long. It managed to, yep, see this battery is only 1.28 volts. That is dead by alkaline battery standards, and still we're able to light this LED. So let's check our voltage across the LED. So we got what, 1.15 at the battery, and across our LED 1.12. So we've got, apparently have even less voltage across our LED than we do from our battery. And the answer, the reason that is not actually the case. What this meter is doing, if you saw how slow it is at actually leveling off and getting a voltage there, it's averaging. All right, so since we're generating alternating current here, and this is actually flickering really, really fast, what the meter sees is it averages it out, and since, you know, in theory we're not actually getting any more power, we're just cycling it to boost the voltage. This would be misleading. So to get a more accurate representation, we're going to use, this is a piece of equipment called an oscilloscope. It has oscillations in the name because that's what it shows. It shows waveforms and oscillations. How am I going to do this? I'll put that there. And we've got, it's got probes here. Little clip lead there, and this is how we'll make our circuit. So this will bind the ground. So this isn't critical, but I'm going to hook it up to the output. I'm going to hook it up across the LED. I'm going to look at that waveform. So bind the ground there. Alright, and we'll steady this guy here. Oh boy, this is not going to work. So, I'm going to have to set this up manually. Stop it. Equipment malfunction. This is not a piece of equipment you want to malfunction either. Oh, that's just the display. The view. We're going to turn off channel 2 for now. And say there, and we're going to set our trigger voltage. Channel 1. Put it there. There we go. Right. Pick up. Bigger. There we go. We'll make it bigger. Right. So what we're looking at, we have a graph here, and so this is our vertical axis is voltage, essentially. And each little division, each little dotted line, according to the scale, is 1 volt per division. And horizontally, each division, our horizontal time base is 250 nanoseconds. So let's get rid of this, and we actually do have a frequency counter running down there. It's hard to see, but this is running at about 1.65 megahertz. So basically what we've got here is an oscillator. It looks a bit like a sine wave. It's a little deformed. If we make it bigger, put it down here. Yeah, it's got some phase variance in it. Let's put that back and trigger so that we're sane still. And let's go ahead and probe the other thing we're interested in looking at how the circuit is. We know that it's oscillating on the output. Let's take a look at the base voltage. I'm going to add a probe here and coupling. And we'll just go there and put you to there. I'm going to probe before the resistor here. All right. What are we looking at? Actually, this is not the same scale, so let's put that at the same scale. Ah, look at that. So, we've got, let me get something to point with. The blue is our transistor base voltage, right? And it's turning, as it's turning on, the output at the LED is turning off. And as that turns on, it charges up the magnetic field in the toroid, and the LED flashes on and turns off, so on and so forth. We've got basic little oscillator here, exactly what we expected, except it is running at a rather high frequency. I don't really like that. So let's slow it down a bit. I've got, let's see, what have I got? To slow this down, I would either have to add inductance in our little, there's no good way to do both of these at the same time. I'd have to add inductance in our little oscillator circuit in our toroid, or I can put in some capacitance. I don't think we've touched on capacitors yet. This is a type of capacitor. It's a ceramic capacitor. Capacitor is basically just a way to store an electric field, an electric charge. It's like a battery, very small battery with very little capacity, at least this one, that can charge and discharge very rapidly. So I'm going to put this in. I'm going to put it between the base on the other side of the resistor and ground. And something interesting just happened to that graph. There's a few things that happened. First of all, let me show you what it's done to the circuit. Right, so we've got our little LED lit up here. I've got the capacitor I'm about to put in, and you can't see both, can you? There's no good way to do this. There we go. Right, so I'm about to add the capacitance, and there we go. Look at that. It got brighter. Why is that? Go ahead and leave it in the circuit, and we'll see what it did to our waveform over here. You'll notice that the oscillations on the base, this is what it was before, and actually let's go and capture that. Let's see if I remember how to do this. Okay. Actually, we care about channel 2. Alright, so we've got our reference there and keep that going. Alright, so purple is the old waveform. I'll go ahead and add that capacitor back in. There we go. Look at that. Significantly different. I'll go ahead and turn off channel 1 so you can see it. There we go. It's not only a proper sine wave now, its period has changed. So since there's a longer period, the waves are longer, and the frequency will be less. It's now reading 750 kilohertz. Turn that off. And our output waveform has changed too. Take a look at it real quick. We'll go ahead and turn off our reference and we'll save. There we go. Take that on. So there's our new waveform and our original one. Look at that. So we've got a longer duty cycle, time where it's on and off, and nearly half the frequency that we did. Since it's switching at much less of a frequency, that should actually be good for our current consumption. Actually, no, this is a proper oscillator, and it is oscillating at about, I imagine this is decimating the AM band. If we were to take a radio, actually. I'll go ahead and pull my radio out, and we'll see what this is doing to it. Maybe no good way to do this, I don't think. Just running it off of a small battery here. Did lead acid. Right. I don't think I'll need an antenna, but what I'll do is I'll just put a little jumper in. And put it close here. I'm not connecting anything, I'm just setting it right next to the circuit. Go ahead and turn that on. And see if I can get this right. You guys can go ahead and unmute your microphones. Right. And let's see, oscilloscope says it's running at 756.4-ish kilohertz. So go ahead and let's see. Ah. I'm reading 756, but that must just be. Oops, wrong way. And actually, if we change this from mode, 756, 7-ish. There we go. Lovely tone. And this is all just noise. Oh, listen to it. This is just me touching things around the circuit. Oh, it's all over the place, as you can see. So it's very sensitive, and this is oscillator. It's a very unstable oscillator. This would not make a very good radio transmitter. Oh my goodness. This is loud. If we took the capacitor out, our frequency would change, but we'd still get 141. 1.41. Oh yeah, there we go. Oh, I've upset it. Oh my, that's beautiful. Oh, that's dreadful. Oh, there we go. So, let's get this out of the way. That is rather annoying. So there we have it. If you'd like to reproduce this, you can build it yourself. These are all parts you can get at RadioShack. Nice little gadget to have around. Make use of some dead batteries. You can get this is a diffused LED, but the LEDs like this, the bright, super bright white LEDs, those would be good for a circuit like this. We can have use it to light your way. Let me try it with this one. See how bright it gets. Yeah, it's really fairly bright. It's very directional. Like a nice little torch. I'll put the diffused one back in. It's actually a smaller one. So I would recommend trying that out. If you don't want to do breadboard construction, we can do a segment on making something a little more permanent. You'll need a soldering iron. You guys can unmute your microphones. I'm going to go and end the broadcast.